We present OmniContact, a novel system for generalizable humanoid loco-manipulation that seamlessly chains reusable meta-skills for robust long-horizon tasks. Before diving into our method, let's ask a fundamental question. What is the optimal interface for long-horizon loco-manipulation planning? To plan complex multi-step interactions, we need a representation that connects high-level goals to low-level control. Let's look at two common choices. Option 1 is to use full human-object interaction states, the complete configuration of the body and the object. This interface is explicit and precise. It tells you exactly what the interaction should look like. But there's a catch: it's extremely hard to generate. Producing full, physically consistent HOI states for every step of a long task is costly and difficult to online generating it. Option 2 goes the other way: a skill embedding or latent representation. These are easy to generate. You just sample a latent code, but they come at a price. They're implicit and imprecise. You lose direct interpretable control over the actual contact and motion. So we're left with a gap. Is there any interface that is, at the same time, explicit, precise, and easy to generate? This is exactly the question that motivates our work, and the contact flow representation is our answer. Contact flow focuses on the essential element of any manipulation, the contact itself. It captures where the hands and feet make contact with an object and how those contact points evolve over time. The same representation naturally spans a wide variety of objects and skills: pushing a box, dragging a suitcase, dribbling a soccer ball, all described through the same unified contact-centric interface. Our framework is built around a single shared representation, the contact flow, which bridges high-level planning and low-level control. It starts at the top level with a vision language model. Given a high-level instruction, for example, arrange the scattered boxes into a heart shape, the VLM decomposes the task and outputs object-level goals: which skill to execute, the initial and target object poses, and the humanoid's starting state. These goals are passed to CFGen, our mid-level planner. Rather than optimizing expensive full-body trajectories, CFGen uses a compact library of hand-designed phase templates. For each phase, it generates keyframes by solving inverse kinematics only when precise contact is needed, interpolates a smooth trajectory between poses, and constructs the contact flow. The contact flow is a sparse set of future body targets paired with binary contact signals. Crucially, CFGen continuously monitors execution and, upon detecting a failure, immediately replans from the current state. This contact flow is then handed to CFTrack, our low-level executor. Trained with reinforcement learning, the policy takes the contact flow targets together with a history of interaction states and outputs whole-body motor actions. A discriminator provides an adversarial motion prior to keep the movements natural, while a tracking reward keeps the robot faithful to the plan. The bottom row shows the real power of this representation. The very same contact flow interface expresses a wide range of behaviors: carrying, pushing, kicking, and pure locomotion. The contact flow generation is in a closed-loop way. When the box is unexpectedly disturbed, CFGen detects the failure and replans on the fly, allowing the robot to reapproach the object and seamlessly resume the task. To train OmniContact, we collected a large-scale human-object interaction dataset captured specifically for loco-manipulation. In total, the dataset contains 1,274 valid sequences, amounting to over 22 hours of motion and 7.2 million object frames, all recorded at a high-fidelity 90 Hz paired capture rate. We retarget these human motions onto our G1 humanoid robot, transferring the captured interactions into physically consistent whole-body references. These retargeted trajectories provide the reference motions that drive both CFGen's templates and CFTrack's adversarial motion prior. Starting from this diverse interaction dataset, we train a single unified low-level policy, CFTrack, which can execute a full spectrum of meta-skills. This demonstrates that OmniContact learns genuinely general Loco-Manipulation skills, robust, reusable, and ready to be chained into longer, more complex tasks. Since all skills share the same contact flow interface, the meta-skills push suitcase and carry box can be chained together seamlessly. CF-Gen simply concatenates the contact flow segments of consecutive skills, while CF track transitions between them without any specialized stitching or retraining. In this case, the robot pushes the suitcase into position, then transitions directly into carrying the box to its target, all in one continuous, uninterrupted sequence. Beyond chaining skills, a truly robust system also needs to handle the unexpected. This is where autonomous recovery comes in. Building on the same meta skills, pushing the suitcase and carrying the box, OmniContact can detect when an interaction has deviated or when the object has drifted away from its goal position. As shown on the right, when the object ends up displaced from where it should be, the robot automatically reapproaches it, reestablishes contact, and repositions it toward the target, all without any human intervention. Finally, we show how OmniContact connects to high-level reasoning through vision-language model integration. We feed the scene information, the set of boxes, their colors, and their positions, to a VLM. The model reasons about the task and decomposes it into a structured sequence of sub-goals: which object to move, which skill to use, where to place it, and, importantly, the matching constraints, such as placing the red letter block on the red target box. This structured output plugs directly into our skill interface. Each sub-goal specifies an object, a carry_box action, a target pose, and a semantic label, which OmniContact then executes. This demonstrates that OmniContact isn't just a low-level controller. It serves as a grounded execution layer that turns abstract language-level goals into precise, contact-rich physical behavior. Thanks for watching. Please scan the QR codes to learn more about our projects.